Green politics and how we deal with energy sparked a lot of discussions lately. For some people, energy harvesting sounds very promising to contribute to that topic. But is this true? How does it work and where does it fit? Let's have a closer look. Grüezi YouTubers, here is the guy with the Swiss accent, with a new episode and fresh ideas around sensors and microcontrollers. Remember, if you subscribe, you will always sit in the first row. Let's start with an overview and later continue with tests of these boards. We have several primary energy sources like coal, uranium, oil, gas, sun, water or wind to produce electrical energy. From there, we can choose two primary routes to our small devices. Either we connect them directly to the power grid, or we use a battery to store energy. And we have a completely different third possibility. We build a small power plant and produce a small amount of electrical energy close to our devices. This video will follow the third route. Let's look at the definition. The word energy harvesting is used for the production of small amounts of energy. Otherwise, we would call it solar or wind energy. There is no clear borderline between the two areas. Both have the advantage that we do not need to change the batteries from time to time. Energy harvesting uses all sorts of sources like sun, wind, mechanical movements, or temperature differences to produce electrical energy. So we can answer the question in the title right now. Energy harvesting cannot solve the energy problem at all, because it is too low power by definition. It is even worse. The energy produced by such a device usually does not offset the energy needed to build it. But why do we talk about it? Because it can be an alternative to battery change for a category of devices, which can be a pain in the A and can induce a lot of cost. Let's assume we have to change the battery once a year, have to calculate with an hourly rate of $30, and expect an average time to change one battery of 30 minutes, we create a cost of $75 per device over its life. 30 minutes is not exaggerated because often we have to drive to the device, maybe have to use a ladder or remove a few things to access the device. You see, it can get expensive quickly. And I did not include a management software to track the needed battery changes. Or imagine your smartphone would not need a recharge and would be always on. Great, I'm in for that. But is this possible? Here I have an old personal device which uses energy harvesting. An automatic watch. It is 40 years old and as soon as I shake it, it starts to run. No batteries needed. By the way, before this invention, the wristwatches had to be charged every day by injecting mechanical energy which was stored in a spring. And guess what? Mr. Perele, the inventor, was a Swiss. Today we would probably call him a maker. So our ancestors also did not like to charge their personal devices every day and solved the problem in their own way. The early electrical energy harvester were these pocket calculators. They also do not need a battery change. And, I have to admit, these were not invented by the Swiss. So let's check if energy harvesting at least solves our smartphone problem. Here I have a few boards which are sold under the topic energy harvesting. In this video I will concentrate on the harvesting of solar energy because energy levels of other sources like mechanical energy harvested by piezo elements or harvesting radio waves using an antenna are too small for my taste. Especially RF energy is fortunately much too low in most areas to be used to power any device. In contrast to all these discussions about 5G antennas, at least where I live. All boards have a chip, one or more inductors, and a few other passives aboard. But what are the other components of such a system? The first component is a small solar cell. Such cells have two issues we have to overcome. First, their voltages are low, especially in low-level light situations. And secondly, they deliver the maximum power at a particular voltage, which, unfortunately, changes with the illumination level. We saw that in video number 142 and 154. You should see now a link to these videos in the upper right corner of your screen. The first problem is solved by a sophisticated boost converter which is capable of starting on extremely low voltage levels, typically 0.1 volts. The second problem is solved by a maximum power point tracker, also called MPPT. This block either uses a fixed voltage to define the MPP, or it measures the actual open circuit voltage of the solar cell and adapts the current to the MPP. The MPPT voltage usually is set to about 70% of the open circuit voltage. This measurement is done every few seconds to account for changes in lighting levels. Very sophisticated. After these two components, the energy is transferred into a storage element, usually a one-cell Li-ion battery or a supercapacitor. Li-ion cells have to be protected against over- and undervoltage. Because modern electronics run on 3.3 or 1.8 volts, we need a buck converter or a low dropout regulator to take the voltage of the battery or the supercap down to 3.3 volts or lower. And because the storage element can be depleted, the MCU has to be warned that it will no more get energy, and after that the load has to be cut off. Like that, critical tasks can be ended and the user can be warned. That's it. But pay attention, not all chips offer all the blocks shown before. Let's now have a look at the different boards, starting with the BQ25504 from Texas Instruments. This is a quite old chip and officially it is no more recommended for new designs, but you still find it on AliExpress. Its MPPT is not sophisticated and uses a fixed voltage. Its output voltage is not regulated and the load is not switched off to protect the battery from depleting. It seems the focus was on getting the most energy out of a source. The battery OK signal is switched on at around 2.8 volts and the maximum power voltage of this board is approximately 3.1 volts. And because the output voltage is the same as the battery voltage, it is not ideal to operate a 3.3 volt device. You could change these voltage levels by exchanging resistors on the board or by using this pin header. The energy harvesting part seems to be very important for the designers of all these chips. All boards show off with how good they are in this end. That they can start extracting energy at very low voltage levels and that the chips are highly efficient. But is this really important? We will see later. This board is outdated and I do not recommend it because it needs a lot of additional elements. The next one, the BQ25570, is also from Texas Instruments. It is more advanced, it has a sophisticated MPPT, contains undervoltage protection and a buck converter. The board I have switches the load on if the battery voltage is above 3.2 volts and charges up to 4.2 volts. So its settings are made for a Li-ion cell. And it has an adjustable buck converter for the load. Unfortunately, this board has an output voltage of only 2.6 and not 3.3 volts. Of course, you can change that if you have good eyes and a steady hand. Surprisingly, the board has an onboard supercapacitor, and if your device only needs minimal current, you do not need an additional storage. As far as I know, there is no balancing of the two cells inside the supercap. A board with most of the needed parts. The only missing detail is the deferred power switching. The status flag sent to the MCU immediately cuts the power. The next one is the LTC3108 from Analog Devices. It needs a coupled inductor for its boost converter. Unfortunately, this part is missing on the board. They did not fill it with the excuse, "You can choose the winding ratio." However, they also did not supply one or two parts to choose from. Like that, the board is useless and you have to purchase the piece separately. No big deal, you would think. But here in Switzerland, the inductor costs a little more than $4. But small quantity surcharge and shipping adds to nearly $20, which was too much for me. If we look at the chip, we find the boost converter. Because I do not see an MPPT, I do not know how this chip manages solar cells. It has two output rails, one for 2.2 volts and one for 4.1 volts. The intention is to run the MCU on 2.2 volts and any transmitter or sensor on higher voltage. The chip does not have a built-in 3.3 volt regulator nor a switch to cut the load when the battery is low. You have to add these parts in your design. All in all, it is comparable to the BQ25504, and because of the lack of one critical part, it does not work when it is delivered. I do not recommend this board unless you have an excellent reason to go for it. Now we come to a chip from the small Belgian company Spiess. They are focused on powering small IoT devices from different sources. I have here two boards with their AEM 10941 chip for solar panels. The overview suggests that this is precisely what we need to power our devices. We just connect a solar cell to the controller, add a battery or a supercapacitor as a storage element, and connect our 3.3 volt MCU, including sensors. Let's have a look at the internals to see if they can keep their promise. Here we find the boost converter, including the mandatory cold start circuitry to make sure it starts at low voltage levels. Then we have a sophisticated MPPT. Next we have the battery protection circuit with selectable maximum and minimum voltages. And we have an adjustable buck converter which can be set to 3.3 volts and even a small LDO for 1.2 or 1.8 volts. These converters are switched off before the storage battery or supercap is completely depleted. And a signal is generated 600 milliseconds before this happens, which gives our devices a chance to send a last message or do other important stuff. All in all, this chip has all the elements we need. The external components are at the minimum. These guys really wanted to provide a complete solution. By the way, the chip even offers a balancing for two serial supercaps, more than I expected. Unfortunately, Jasper, a Dutch developer, used this chip to build two different boards, one optimized for Li-ion batteries and one for supercapacitors. And he won the Hackaday prize for this design. So let's check it out. The sun is shining outside. The bad news first. All these solar panels cannot be used because none of the energy harvester boards supports input voltages above 5 volts. The BQ25504 even runs only up to 3 volts. And all of these panels have open voltages above 5 volts in the bright sun. But I can comfort you, at the end of this video we will find a useful purpose for all of them. This is why I bought some cheap polycrystalline single cells for this test. Here I connect 4 cells in parallel and here 2 in series. Today I can also use my new Joule scope to measure current and voltage across the solar panel. And really, from time to time, the chip opens the circuit to measure the open cell voltage. Then it adjusts the current according to the MPPT strategy. During this short time, nearly no energy is extracted. But afterwards, all the more because it works on the optimal point. On average, we get around 80 milliwatts from this two-cell configuration in bright sun. And the supercap charges up till around 4.5 volts. Then it stops charging. The load only gets switched on if the battery voltage is above 3.9 volts and stays on till it is 3.6 volts. So we only have a usable voltage swing of around 1 volt, which is not a lot. This is because the battery voltage has to stay above 3.3 volts plus the dropout of the regulator. You see, the energy produced in summer and in full sun is small. And in my lab, despite the bright overhead LEDs, I hardly get any power. Jasper, the builder of the boards, confirmed that artificial light is nearly useless for energy harvesting. So far we learned, energy harvesting using small solar cells works. The boards with the most modern chips are easy to use. They contain the needed components. In the bright sun, we get a few milliwatts of energy. In my lab, we hardly get any power. I know my cells are not optimized for indoor applications, but better panels at even more cost. The efficiency and the capability to extract energy at the lowest levels often is less important than the placement of the device. 1 minute in bright sun can create more energy than the rest of the day. The boards are costly compared to normal power supply boards. If you are interested, you can also go to a page of Limkin, who did some testing during winter here in Europe, indoors but with sunlight through a window. The energy levels he was able to harvest also were minimal. As usual, you find all the links in the description. What are typical uses for energy harvesting? As a Swiss, I like this example, even if it's used in Australia, a cow tracker. Do you see the ear tag? Here a close-up of the tag where you see the small solar panels. This device sends every 30 minutes a position message to a LoRaWAN gateway. So no escape for the cows. And rumors say that they even track the performance of the bulls with these devices. Obviously, there is no privacy in this business. If you have a similar project, energy harvesting might be a solution. But be prepared to calculate in microwatts and not in milliwatts. For all other demands, it is still cheaper to increase the size of the solar panel. For $20, you should get a powerful panel for your project, if you have enough space to place it, of course. By the way, the next version of the cattle tag seems to go a similar route and uses a much bigger solar panel. I think for the next years, energy harvesting will be a niche application. With more and more low-power microprocessors and sensors coming to the market, this might change. But I forgot the board with the LTC3588. It is mainly advertised in conjunction with piezo elements. Therefore, it allows a much higher input voltage. As you see, I tried hard to produce some energy. In the end, I probably better would have used a dynamo to produce electricity. With piezo elements, it is tough to get even microwatts. Nothing for me. Summarized, energy harvesting does not save the world, nor will it ever charge your smartphone. It is a niche technology for small, low-power devices. It mainly saves maintenance cost because you do not need to change batteries. Most boards on AliExpress are not ideal because they do not contain a whole solution. You have to add functions or even parts on your own. Newer chips are available which are closer to a ready-made solution. Examples are the BQ25570 and especially the AEM10941. There are still constraints like a small usable voltage range for supercapacitor or the number of serial solar cells. If you depend on harvesting also smallest voltages, your risk is quite high to deplete the storage from time to time. The energy is very low, especially indoors. In purely artificial light conditions, it's even worse. If you are not space or weight constrained, go for a bigger solar panel. It is cheaper and less risky. So I can still use all my bigger solar panels. Lucky me. If you want to try energy harvesting, I suggest using Jasper Sport. It is a complete solution. Just select the right one and add a solar panel and storage. I hope this video was useful or at least interesting for you. If true, please consider supporting the channel to secure its future existence. You find the link in the description. Thank you. Bye.